Hello everyone. Today we are going to analyze this beam using flexibility matrix method. In this beam there are two spans, span AB and span BC. In the span AB there is uniformly distributed load 36 kN per meter. It is acting for the whole span. In the span BC, there is a concentrated load 72 kN. It acts at a distance of 2 meter from the support B. Span AB is 4 meter long and its moment of inertia is 2I. Span BC is 6 meter long and its moment of inertia is I. Now let us find the degree of static indeterminacy. The number of unknown reactions and moments are 3. They are the vertical reactions RA, RB and RC. The available equilibrium equations are 2. The degree of static indeterminacy will be 3 minus 2, so it will be 1. From this beam, let us release RB. You can see that from the point P, I have removed RB. Now this is a simply supported beam. This beam is called as a released structure. To find RA, let us take a moment about C. In this case, we have to follow right hand side rule. Clockwise will be positive and anti-clockwise will be negative. RA is acting in the clockwise direction, so that it will be positive and the distance is 10. So 10 RA. The uniformly distributed load is acting in the anti-clockwise direction, so that it will be negative and the distance is 4. Then we have to open a bracket. The distance 4 upon 2. Then we have to add the remaining distance, which is 6. The point load is acting in the anti-clockwise direction, so that it will be negative and the distance is 4. For RA, we will get 144 kN. Then by applying this rule, we can find RC. For RC, we will get 72 kN. Now let us draw the coordinates diagram. In this analysis, there is only one coordinate, that is RB. This is the coordinate because we have removed RB. We know the formula which is used in the flexibility matrix method. In this formula, P will be the final moments or reactions. Here there is only one reaction, that is RB. So P will be RB. In the point P, there is no sinking or settlement of the support. So delta matrix will be a zero matrix. So this matrix will be 0. So that we will get this equation. To find the displacements delta and delta L, we are going to use unit load method. In the unit load method, we have to make sections. Let us take the released structure. Let us keep this point as a D. In this beam, there are 3 different parts, AB, BD and DC. So we have to make 3 sections, one in AB, one in BD and one in DC. You can see that I have made 3 sections, one at AB at a distance of x from A, one in BD at a distance of x from C, and the last one at a distance of x from C. Now let us make a table. In the table, first let us enter the members. There are 3 members, AB, CD and DB. For the first section, the origin is A, and for these 2 sections, the origin is C. For AB, the limit is 0 to 4. For CD, the limit is 0 to 4. And for DB, the limit is 4 to 6. Now let us enter the flexural rigidity. For AB, the moment of inertia is 2I, so the flexural rigidity will be 2EI. For CD and DB, The moment of inertia is I, so the flexural rigidity will be EI. Now let us find the moment M in the section in AB. We are going to find the moment from the point A. In this case, we have to follow right hand side rule. Clockwise will be positive and anti-clockwise will be negative. The vertical reaction RA is acting in the clockwise direction, so that it will be positive and the distance is x, so it will be 144x. The UDL is acting in the anti-clockwise direction, so that it will be negative. We know that with the UDL, we have to multiply the distance and then the distance by 2. After simplifying this, we will get this. Let us enter this inside the table. Now let us find the moment M in the section in CD. We are going to find the moment from the point C. In this case, we have to follow left hand side rule. Clockwise will be negative and anti-clockwise will be positive. RC is acting in the anti-clockwise direction, so that it will be positive and the distance is x, so it will be 72x. Now let us find the moment in this section. RC is acting in the anti-clockwise direction, so that it will be positive and the distance is x, so it will be 72x. This load is acting in the clockwise direction, so that it will be negative. For this load, we have to take this distance. This distance is x minus 4. After simplifying this, we will get 288. Now we are going to find the moment M. For that, we have to remove all of the loads from the beam, and then we have to apply unit load in the direction of RB. Taking moment about C, let us find RA. RA is acting in the clockwise direction, so that it will be positive and the distance is 10. So 10 RA. The unit load is acting in the clockwise direction, so that it will be positive and the distance is 6. For RA, we will get a negative value. That means the assumed direction is incorrect. We assumed that it would be acting upwards, but actually it is acting downwards. So we have to change the direction. Here I have changed the direction of RA. By applying this rule, we can find RC. For RC also, we will get a negative value. That means the assumed direction is incorrect. Here I have changed the direction of RC. Let us find the moment M in the section in AB. RA is acting in the anti-clockwise direction, so that it will be negative and the distance is x. Let us find the moment in CD and DB. About both of these two sections, RC is acting in the clockwise direction, so it will be negative and the distance is x. Using this formula, we can find delta L. For AP, the flexural rigidity is 2EI. So in the formula, instead of EI, we have to apply 2EI. Using the calculator, we can do these integrations. For delta L, we will get this. Then using this formula, we can find delta. For delta, we will get this. In these two matrices, we have found both of the members. We can apply them. We can find this inverse. We have to write the member upside down. Since there is only one member inside the matrices, we can keep the members outside. No need to use the matrices. Then we can eliminate EI. So for RB, we will get 152.5 kilonewton. Now let us take the original beam. By taking moment about C, we can find RA. For RA, we will get 52.5 kilonewton. By applying this rule, we can find RC. For RC, we will get 11 kilonewton. From the point A, let us take moment about B and find the moment at B, MB. Let us assume that it is a hugging moment. RA is acting in the clockwise direction, so that it will be positive and the distance is 4. The UDL is acting in the anticlockwise direction, so that it will be negative. With the UDL, we have to multiply the distance and then the distance by 2. About the span AP, MP is acting in the clockwise direction, so that it will be positive. For MP, we will get a positive value. That means our assumption is correct. MP is a hugging moment. Now we are going to draw the bending moment diagram by superposition method. For that, first we have to draw the free moment diagram. We have to consider every span as a separate simply supported beam. Then using these formulas, we can find the moments and draw these two diagrams. Then using the moment at B, we can draw the end moment diagram. Combining both of these two diagrams, we can draw the bending moment diagram by superposition method. Using the right hand side rule, we can find the shear force values. Here you can see the shear force diagram. In this point, the shear force becomes 0. In this point, there will be maximum positive bending moment for AB. We can make a section in this point and find the distance. You can see that in that point, I have made a section at a distance of x from A. We know that in this section, the shear force is 0. Using right hand side rule, we can find the shear force. For x, we will get this. Now using the right hand side rule, we can find the maximum positive bending moment. The points A and C are the simply supported ends, so the moment will be 0. Using the right hand side rule, we can find the moment at B, which will be minus 78. We have already calculated that. Now let us use the left hand side rule and find the moment at D. RC is acting in the anticlockwise direction, so that it will be positive and the distance is 4. For the moment at D, we will get a 45.6. This is the proper bending moment diagram. If we make this diagram upside down, that is called the bending moment diagram on the tension side. In these two points, the bending moment becomes 0. These are the points of contraflexure. We can make sections in these 2 points and find the distances. First, let us find the distance in the span AB. In the span AB, I have made a section at a distance of x from A. Using the right hand side rule, we can find the distance. Now let us find the distance in the span BC. I have made a section at a distance of x from C. Using the left hand side rule, we can find the distance as 4.72 meter. Now we are going to end this session. Thank you for watching.